Okay guys, in this video we are going to go through speed control of shunt DC motors, which is the second part of the lesson 3, which is on DC motors. As we should understand that the ability to be to control the speed of DC motors is a very important one, because by achieving the speed control, we can meet the requirements of the applications that we have. For example, in some applications we might want to run the motor at higher speeds. In some other applications we might want to be able to gradually change the speed, either increasing it or lowering it down. Okay? So it's really important for us to be able to control the speed of DC motors. Okay, speed control of shunt DC motors. Basically, there are two common ways that are used to control, okay, which are: first is by adjusting the field resistance, or RF, and the second method is by adjusting the armature's terminal voltage, or VT. And additionally, there is the third method, which is less commonly used, which is by adding a resistor in series with the armature winding. By inserting a resistor, extra losses will be incurred, and that's why this method is not commonly used, because of that extra losses introduced when we use this method. Especially in heavy duty applications where the current gets very high, and adding this resistor really doesn't help. So that's why again, this third method is not commonly used. Okay, we will look at each of these techniques in more detail in the following slides. Okay, in this slide I will walk you through the first technique, which is adjusting the field resistance, or RF. How changing the value of RF can lead to the change in the speed. Now let's assume that RF is increased. What will happen to the speed of the motor? If we refer to the schematic diagram on the right hand side, or we call it the equivalent circuit of this shunt DC motor, if you see this part here, the field circuit, which is here, okay, across this field circuit we've got VT. VT is applied to these two terminals, okay, which is practically the same thing as applying this voltage across this, because they are these pairs of points are connected. Okay, so we've got VT across here. I delete this. I remove this. Sorry. Okay, so we've got VT across here. And therefore, the current that goes through the field path, which is IF, will be the voltage VT divided by the total resistance of these two resistors. You've got R adjustable and the RF. So again, the field current, which is IF, which is the current flowing through this path here, is VT over the sum of these two resistors. So if I write it down, VT, it's IF instead. IF is equals to VT divided by R plus RF. R adjustable plus RF. This variable resistors or resistance plus RF. So in this slide here actually it's supposed to be RF plus R adjustable, which is actually commonly or in many places we just simply call it RF, which is referring to the sum of these two resistances. Right, so we've got this equation, IF is equals to VT over R adjustable plus RF. So what will happen now if we increase RF? Yeah, you can see from these equations, because RF is in the denominator, when we increase RF, assuming that VT is constant, IF will simply get reduced. It will be reduced. So this is what is referred by the first point, which is increasing RF causes IF to decrease. Okay, so that's the first steps done. Now let's have a look at the second one. What will happen when after the IF is decreased? Okay, just delete all this first. Right. So now what will happen when IF is decreased? Now we refer to the magnetization curve, which is this curve here. Okay. This curve shows us the relations between magnetic flux density and this capital F denotes the MMF, magnetomotive force. And if you remember, F or this MMF is equal to number of turns times current. Specifically, this current here is the field current, IF. Okay. So actually we can replace this MMF. Yeah, if you like, I remove this MMF. You can put down here IF, and the unit is ampere. Yeah. This will retain the shape, although the scale might be changing. Yeah. But the shape of this curve will stay the same. Yeah. So now we have magnetic flux density, yeah, here on the y-axis against IF on the x-axis. And then, so now what will happen, again, to continue our discussion on the effect of changing the field resistance, if IF is decreased, yeah, you look at we look at number 0.1 here. When IF is decreased, which means that on the x-axis we go from the right to the left, yeah, and then we can see that decreasing IF will result in the decrease in the flux. So the flux will also decrease. Yeah, you can see, for example, it will be, we are going from here towards 0. Okay, so from right to the left, the flux is decreasing, especially within this linear region here. Okay, right. So again, decreasing IF will result in the decrease in the flux or the magnetic flux density. Oh, sorry, just magnetic flux, not magnetic flux density. Okay. Yeah, if I mentioned magnetic flux density before, it should have been flux rather than magnetic flux density here. Yeah, magnetic flux density is denoted by capital B, not the Greek pi. Right, now we have a decrease in the flux. Now what will happen? If you look at point 3, decreasing flux will lower the internal generated voltage or EA. As because I think if you all remember that EA is equals to K flux omega m. Alright, I'll do it again. EA equals to K into flux into omega m. Yeah. So if you reduce the flux, then EA will be reduced as well, right? I hope that's clear. Right, now what's next? When the EA is decreased, IA or the armature current will also be decreased, yeah? Following this equation here, yeah? which you can derive by using this again, this equivalent circuit. Yeah? Where is IA? IA is here. Yeah? So you can see from here that the IA is equals to the voltage across RA, yeah, this voltage divided by RA, and this the voltage across RA is equals to VT minus EA. Yeah? So again, IA is equals to VT minus EA over RA. So when EA is decreased, again here is IA. When EA is decreased, VT minus EA will be increased, and therefore IA will be increased as well. Okay. Let's see if I can change this. Can I change it to? Okay, never mind. Maybe I will try or learn the technique again later. Right. Now EA is already increased. Sorry, IA is increased. Yeah, this IA. Then if you look at step number 5, yeah, when IA increase, then the induced torque or the torque generated by the motor will also be increased. Yeah? Again, simply we just follow this equation here, where the induced torque, yeah, this induced torque is equal to K flux or K pi IA. Yeah? Again, this constant times the flux and times the armature current IA. Yeah? Okay. Now we should underline here that the change in IA, yeah, this one, is dominant, yeah, over the change in flux. Okay, what does it mean? Here, because we've got two conflicting effects, yeah? Two conflicting effects where the change in the flux, yeah, or in this case the flux is decreased, it will lower down EA, and therefore it will lower down IA. Yeah? However, let me rephrase that one again. Yeah? We've got the change in IA, the armature current, more dominant over the change in the flux pi, which is referring to these two variables here. Okay, because the induced torque is equals to K pi IA. Yeah? The IA is increased. Yeah? IA this omega m is increased, yeah, that we learn from this, yeah. So when omega m is increased, EA will also be increased, right? Then number 8, the increase in EA will cause a decrease in IA. Yeah. Again, because IA is equals to VT minus EA over RA. Okay. So when the EA is decreased, IA will be increased. Okay. Right. And then finally, decreasing IA, yeah. Oh, sorry, I got it the wrong way around. Sorry. EA is increased. Yeah, here EA is increased, and therefore IA is decreased. Right. And then point number 9, decreasing IA, yeah, IA is decreased, will also decrease the induced torque. Okay, because again the equation is the induced torque equals to K times pi times IA. Okay, right. Okay, so decreasing IA will decrease the induced torque, or the torque generated by the motor. Right. So this will keep repeating, yeah, this loop. Yeah, the induced torque will be less, and then therefore the difference between the induced torque and the load will be decreased, and the acceleration will be less, so the change in the speed will be less, yeah? But the speed will still go up. The speed go up, and then it will follow again the same steps, 6, 7, 8, 9. Then when we reach number 9 again, the induced torque will be even less, yeah? And then you start from number 6 again, and when you reach number 9, the induced torque will be even less, until the induced torque is reduced so much that it becomes equal to the load again, yeah? And this will happen at a higher speed, yeah? Okay, because we learn this during this loop here, the speed keeps increasing, yeah? So that's why at the final state, at the new steady state condition, we will have a higher speed while the induced torque becomes equal again to the load, yeah? So we reach a new balance here, yeah, at a higher speed. So basically this is what happens when you change the field resistance. If you increase the RF, IF will be reduced, and the final outcome is that the motor will run at higher speed. And the opposite will happen, i.e., if you reduce RF, or the field resistance, then the speed of the motor will be reduced. Okay, I think that's enough for this slide. Okay, still with the first technique, which is changing the field resistance to control the speed of the DC motor, there is something that we need to watch out here when we design the speed control by using this technique. Yeah, the effect of increasing the field resistance on the output characteristics of a shunt DC motor can be seen on the graph here on the left hand side. So this graph actually is also represented, this characteristic is also represented by the equation on the right hand side, which is this equation here. This equation has been derived before, and then you can refer to one of the previous slides that we had gone through. Right. This equation shows us the relation between omega m, which is the speed of the motor, and the induced torque, which is plotted in the graph. Omega m on the y-axis versus induced torque on the x-axis. And this equation, if you remember, is a line equation. Is a line equation where you have the gradient. This is showing us the gradient, and this is the bias. Okay, so when we change the field resistance or RF, this field resistance or RF, when we increase it, we know that the field current will be lowered, and therefore the flux is also lowered. And you can see from these equations, when the flux is lowered, first the bias will be larger. This bias here will be larger, and that's why you can see the line actually shifted. On the graph, the line is shifted up, right? Okay, and secondly, when the flux is reduced, the gradient also affected. The gradients becomes larger, but it's negative, and that's why on the graph you can see the second line on the top is steeper compared to the first line at the bottom here. So this is how the changing of the field resistance will have the effect on the output characteristics of this shunt DC motor. On the next slide, we will see what is the thing that we need to watch out. Right. Now, if you if you look at the graph, this graph is similar to the graph on the previous slide. It's just the difference is now we extend the two lines. We've got this first output characteristics, and then we've got the top one, which is the second one. But now if we extend the two lines will cross each other at this point, and it has an intersection, and then if you keep extending it so that they touch the x-axis, you will see that there is a difference between the area on the left hand side here and the area on the right hand side here. Okay, on the left hand side, when the RF is increased, the outcome is that the omega m, or the speed of the motor, is larger. The motor becomes faster. However, on the right hand side, on the region here, this region is the opposite. When RF is increased, the speed is actually lower. Okay, so this is something that we need to watch out when we design speed control by using this technique. Yeah. So we want to avoid this from happening. We don't want the motor to run in this region. Yeah. So we want to keep the motor to run in this region. Yeah. Okay, so we need to make sure that we know what is the limit. Yeah. We cannot keep what we call changing the current, yeah, or the load, so that it exceeds this limit here. Okay, yeah, so this is something we need to watch out when we use this technique. Okay, the reason why this happening is because of this, that you can read from the second bullet point here. This is happening because the increase in IA is no longer large enough to compensate for the decrease in the flux. Yeah. i.e., the increase in IA here and while the flux is decreasing, so these two effects are conflicting. One is trying to increase the induced torque, and the other one is trying to reduce the induced torque. But when it's running in this region, yeah, actually the flux, yeah, the reduction in the flux becomes more dominant, and therefore now the induced torque is less, yeah, is lower, and therefore that's why then the motor actually slows down instead of speeds up. Yeah. Okay, so now we have the second method for controlling the speed, yeah, which is changing the armature voltage. And remember that the notation for armature voltage is VA. Okay, then if we again look at the schematic diagram on the right hand side at the top, which is the equivalent circuit of a shunt DC motor. Yeah, again this is a shunt DC motor, but now we have a box added to it. Yeah? This box in red here, which is a variable voltage controller. Yeah? Well, we introduce or we add this box to have uh, the ability to control or to change the armature voltage VA independently to VT. Yeah? So by having this controller, again we can change VA without affecting VT. Yeah? So again we can change VA independently. Yeah? And by having this capability, we can then use this technique, yeah, which is changing the armature voltage for speed control. And in effect, actually what we have now is similar to a separately excited DC motor. Yeah. If you remember, with the separately excited DC motors, we have an external voltage source that will allow us to have a separate supply for the armature circuit. Yeah? So we have two power supplies, one for the armature circuit and the other one for the field circuit. So in effect now that's what we have. Yeah? We have VA and we have VT that we can control separately. Right. Then how this method works? Okay. Let's assume now we increase VA. Yeah. We increase VA. So what will happen? Now, if you look at the first sub bullet point here, an increase in VA will increase IA. Yeah. Which is, I think, is quite obvious. This increase in VA yeah, if you look at the schematic diagram, will result in the increase in IA because IA is simply VA. Oh, sorry. Hold on. IA is this voltage here minus EA. Okay, sorry. I think I got it wrong. Right. This slide is wrong actually. Yeah, it's supposed to be IA. Yeah, I write it down here, equals to VA minus EA over RA. Yeah. Okay. So this voltage on the right hand side of the resistor minus the voltage on the left hand side of the resistor RA over RA. Yeah? So the voltage difference across RA divided by the value of RA, that will give you the armature current IA. Okay. So this is not exactly right. Yeah, it's supposed to be VA here. Okay, now so you've got an increase in IA, and then what will happen next? If you look at the second one here, second sub bullet point here, the increase in IA will increase the induced torque. And again, I think this is pretty obvious because induced torque is equal to K pi IA. Yeah? The constant times the flux times the armature current IA. Okay, so now our induced torque is increased, and then the next sub bullet point, the increase in the torque will make the this induced torque higher than the load, yeah, because the load has not changed, and the increase in the induced torque make it higher than the load, and therefore you've got acceleration. The motor will be subject to acceleration, and therefore its speed will go up. Yeah, so the omega m will be increased, and in turn the increase in the omega m will cause an increase in EA, because EA is K times flux or pi times omega m. Yeah, when the omega m is increased, EA also increase. Yeah, and what happens next? The increase in EA, or the internal generated voltage, yeah, will cause a decrease now. Yeah? A decrease in IA. Yeah. Again, the equation is the same as we've seen before. That IA equals to, again, this is supposed to be VA rather than VT, minus EA divided by RA. Now you've got a decrease in IA. This will cause a decrease also in the induced torque. Okay, right. So when you've got the decrease in the induced torque, it means that the acceleration, yeah, remember that before we have this acceleration because of the, yeah, if you refer back to this step here, because of the difference between the induced torque and the load, you have the acceleration. But now the induced torque has been decreased, which means that the acceleration is also decreased. Yeah? So the change is in the speed is not as fast as before. Yeah? The speed is still increasing, but not as fast as before. Yeah. Okay, and this repeats itself. Yeah, it keeps going in this loop. If you like, it's going in this loop. Yeah. So the induced torque will be getting lower and lower until eventually it becomes the same as the load again. Yeah. So, and then when it becomes the same as the load again, the omega or the speed will be constant again, yeah, because there is no difference in the torque, there is no, it means then there is no acceleration, and therefore the speed becomes constant again, yeah. It has reached the new steady state level, yeah, which is higher than before. Why is it higher? Because we've seen from before that when we change or when we increase the VA, the armature voltage, the sudden effect was that the induced torque becomes higher, and then therefore you got acceleration, but this acceleration is not constant, it's getting lower and lower, and eventually the motor will reach a new steady state speed which is higher than before. Okay, so again, in summary, uh, when you increase the VA, what you will get is higher speed, and obviously vice versa, if you decrease VA, what you will get is a lower speed of the motor, yeah? And it's also shown on this graph here, yeah, on the right hand side. Okay, so VA2 is higher than VA1, which means that the armature voltage has been increased, yeah, from VA1 to VA2, and as you can see from the plot that the speed, yeah, omega m, has been increased, yeah? So there's a change or a shift of the output characteristics, yeah, from the bottom line to the top line. And what we should notice here as well is that the gradient stays the same, yeah? i.e. it doesn't become steeper or less steeper, but the gradient stays the same, yeah? It's only shifted up, the line is only shifted up if you use this method, unlike the previous method. That, if you remember, in the previous method, when you change the field resistance, it's not only shifting the line, but it's also changes its gradient. Okay, so this is this technique changed the output characteristic in a different way compared to the previous technique. Okay guys, now we have our third technique here, which is inserting or adding a resistor in series with the armature circuit, yeah? So bear in mind that now we are inserting a resistor in series with the armature circuit, and it's not the field circuit. Okay, right. Again, if you look at the schematic diagram or the equivalent circuit of the motor, then this resistors that we are adding here in this technique is actually this resistor here. You can see in the schematic diagram, yeah, the one that I've just circled in red, that is the resistor that we add when we want to use this technique. Okay, now again, for the characteristics of this motor, the equation is given here, which is again, this is not our first time to see this equation. This equation has come out again a few different times now, and again, this is representing the characteristics of this shunt DC motor, yeah, which is again showing us the relation between the speed and the torque, yeah, which is what we need when we want to produce output characteristics. Right, and if you remember, this is a line equation, yeah, with the bias and the gradient. Right, so when we change, again, when we insert, if you look at again the schematic diagram, when we insert this resistor, yeah, this new resistor here, effectively we are changing the armature resistance, the total armature resistance, yeah, which is in this case actually we are changing this value here, right? Okay, so we are only affecting the second element in the equation. We are not changing the bias. This bias here is not changed at all, yeah. And therefore when we plot the output characteristics of this motor when we use this technique is can be seen just like what we see here on this graph at the bottom here, yeah? You can see that the point here when the torque is 0 has not changed, yeah? So this bias is constant, is not affected by this method, yeah? The only thing that changed, as you can see, is the gradients, yeah? The line, as you increase RA, yeah, as you increase RA, the line becomes steeper and steeper, yeah? Here RA2 is higher than RA1 and RA3 is higher than RA2, RA4 is higher than RA3, which means that we keep increasing RA, the armature current, and the lines or the output characteristics line becomes steeper and steeper, yeah? Okay. Okay, now if you read the second bullet point, this method is wasteful method of speed control since losses in the inserted resistors is large, yeah? Okay, if you look at again the equivalent circuit or the circuit diagram here, when you add these resistors, yeah, so your total armature resistance becomes higher now, and we know that what we call why I cannot delete this, okay, yeah, the losses in the armature circuit is basically IA squared RA, yeah? RA being the total RA and the new inserted resistor, yeah? So this is actually the RA. Okay, and this IA depends on the load. As the load is higher, then your IA will be higher as well, yeah, in general. Okay, and therefore the losses will be even higher, and therefore we don't actually like the RA being high or higher, yeah? We like to ideally keep it low, yeah? But if you use this technique, you like it or not, you need to insert a resistor, which means that RA will be increased, yeah? And that's why that in general this technique is not desirable, yeah? You want to use other techniques. And why do we have this as a technique? You can see in the third bullet point, because of some consideration, yeah? For example, if budget is a limitation, yeah? So if you want to keep the solution low, generally speaking, this method is more cost effective compared to other, which means it's a cheaper solution compared to the others. And another reason that this technique is used is when the motor spends almost all its time operating at full speed. Yeah, the key word here is full speed. When it's running at full speed, then the load becomes minimum, yeah? And therefore IA is also minimum, yeah? And therefore you can keep the losses still low, yeah? So these two are basically the reasons that you may have when you decide to use. Okay, we have discussed the three different methods that we use with shunt DC motors. However, we may have the fourth one, yeah, which is actually a combination of the first two techniques that we have discussed, which are the field resistance variation and the voltage or the armature voltage variation. Yeah. So by changing the field resistance and by changing the armature voltage, and we combine these two techniques together, and this slide shows us why this technique is introduced. Okay, in the RF control method, yeah, the lower the IF or the field current, which is directly controlled by adjusting the RF, will make the motor runs faster and vice versa. Yeah? Yeah. So how do you lower the IF? You lower the RF by increasing RF. Yeah? And if you do that, the motor will run faster. And on the opposite, if you increase IF, yeah, if you increase IF by changing the field resistance, yeah, i.e. you lower the RF, then the motor will run slower. Yeah. So here the field resistance variation or the field resistance control is actually used in this region here. Yeah. And then again here, if you lower IF is the motor will run if you lower IF, the motor will run faster. So it's going this way. This way the IF is getting lower. Yeah? And vice versa, when you go that way, IF is actually getting higher. Okay, so from within this region, yeah, if you go from left to right, it means that IF is decreasing. If you go from the right to the left, IF is actually increasing. Yeah? Okay, now if you look at the second bullet point here, there is limit on the minimum speed, yeah, where IF is maximum or at rated current. Yeah? Okay, again, if you look at the graph, this IF, obviously there is limit. You cannot keep increasing IF. Yeah? There is a limit where you cannot increase IF anymore. Yeah? If you keep increasing the IF, then the field winding might get too hot and the insulation will break down. Yeah? So you don't want that to happen. There's a limit, which means that again, if you look at the graph here, as you go from the right to the left, IF is increasing. Yeah, IF is increasing until it reaches the rated speed of the IF. Yes, so you cannot increase the IF any longer. And when you reach that, you are actually at this base speed. Okay. If you look at the third bullet point, if a motor is running at its rated terminal voltage and rated power and rated field current, then it will be running at rated speed, its rated speed, or another name for it is the base speed, which is this. Yeah, you look at the diagram, is the end base. Yeah, the rated speed or the base speed, the same thing. Okay? So you reach this point here, yeah, this knee, when the IF is at the rated level. So you cannot reach IF anymore, which means that, what does it mean? It means that if you use this RF control, yeah, you can only run the motor within this region. Yeah? You cannot increase IF anymore so that it enters this this region here. Yeah? You cannot, yeah? Because the IF will be too high. Okay, so this is what is actually stated in this fourth bullet point. Yeah? RF control can control the motor for speeds above the base speed but not below. Yeah? As IF is already at the maximum at the rated speed. Yeah? Okay, so now for the region shaded in pink here, yeah, or red, we need to use the other control method, which is the VA control, VA variation control. Excuse me. Okay, in VA control, yeah, the next bullet point, the higher VA, the faster the motor will run. Yeah, and then we know this before. Yeah, as VA is increased, VA is increased, the omega will also increase. Yeah? Okay, so as the VA is higher, as the VA is increased, the motor will run faster. Okay, however, again there will be limit. Yeah, the limit is the rated voltage. Yeah, so you can increase VA until it reaches the rated voltage. You cannot go beyond that. Yeah. What does it mean? It means that there is a maximum speed that it can reach if you use this method, yeah, which is the N base, the base speed here. Yeah. So this is the maximum. So it means that within this region, yeah, that I circle in red here, you can use this VA control technique, but on the other region, the next one, yeah, maybe I change the color. I'll use green. Yeah, for the area or the region that I circle in green here, then you will need to use the second, or in this case the first technique. It was the field resistance variation technique. Yeah. So as a summary, what we find, if we combine these two techniques together, then we can run the motor in all this region. Okay, which is great, isn't it? Because now your range of speed becomes so vast. Yeah? Yeah? You are not limited to only one part, but you can have all this range for the speed. Yeah? And which is summed up in this the last bullet point, that combining these two methods on the same motor will give greater speed variation control of up to 4 to 1 or more, 40 to 1 or more, which means that the high speed can be 40 times higher than the lower speed. Yeah? So you've got a very large range when you combine these two methods. But obviously the drawback is that your controls becomes more complex because you have to use two techniques at the same time, yeah, or with the same motor. Okay, so yeah, again the advantage is that you have a wider range of speed, but the okay, so in summary, in this lesson we have learned 3 different techniques that are used in speed control. 2 of them are more common, which are the RF and VA variation, while the third one, which is inserting a resistor in the armature circuit, is less common due to the additional losses that it has. And the second point that we learned from this lesson is that we can get a very large range of speed by combining the first 2 techniques, which are the RF and the VA variation techniques. Okay, thank you.